All right, hello, welcome to this week's Math 2414 weekly review. This week we're going to be covering section 11.6, which covers, excuse me, absolute convergence and the ratio and root tests. And then we have section 11.7, which is essentially just going to be strategies for testing for convergence and divergence. So let's go ahead and get started with section 11.6. So in section 11.6, we introduced the concept of having absolute convergence. So usually what we've said before is that a series can just be convergent if the sum has a limit. Well, there's actually a little bit more to this now. This is where absolute convergence comes in. So absolute convergence by definition, absolute convergence occurs whenever your series A sub n, that will be absolutely convergent if the absolute value of that series is also convergent. And then we also have, since we have absolute convergence, we also now have something what is called conditional convergence. So conditional convergence what that one means is that our initial series is still convergent, but it doesn't meet the criteria to be absolutely convergent. So typically whenever we see conditional convergence, we're mainly going to see that whenever we have alternating series. So that's just a kind of a big thing to keep an eye out for whenever you are working with absolute and conditional convergence, just mainly because alternating series are going to be the main one where if you take the absolute value, that actually can make a really, really big difference. So just keep that in mind. So just as a quick little brush up, we're going to go ahead and do an example to determine whether or not a series is absolutely or conditionally convergent. So in this example, we have the series from n goes from 1 to infinity of -1 to the n minus 1 over the square root of n. So typically whenever we're going to figure out if a function or if a series, is absolutely or conditionally convergent, usually go ahead and test for absolute convergence first. So what we're going to do is we're going to go ahead and take the absolute value of this. So we can see that we're going to always have some power of 1 on top. So when we take the absolute value, we're going to be left with series from 1 to infinity of 1 over square root of n. Well, we can go ahead and look at this and see that this is a p-series. And we have a power of 1/2. And of course, whenever we have a p-series, we need that to be, we know this is going to be less than 1. So therefore, that's going to have to diverge. So this means that it is not absolutely convergent. But from here, we can still look to see if our series is conditionally convergent. So whenever we do, so in this example, we have an alternating series. So what we can do is we can apply our alternating series test. So if we look at this, if we look at this absolute value of 1 over square root of n, we can see that that's going to be decreasing, or essentially 1 over square root of n plus 1 is less than or equal to 1 over square root of n. So therefore, our first criteria is met for alternating series. And then we now have to just check our second criteria, which is that our limit goes to 0. So if we take our limit as n approaches infinity of 1 over square root of n, we're going to get 1 over infinity, which is 0. So therefore, our second condition is met. So therefore, we can say that this series right here is conditionally convergent. So conditional versus absolute convergence, that's actually a pretty simple concept on its own. So now we can go ahead and move on to our new test for this week. So our first new test that we're going to go ahead and cover in this section is going to be our ratio test. So our ratio test has 3 parts to it. The first part states that if the limit as n approaches infinity of the absolute value of a to the n plus 1 over a to the n is equal to some finite value L, and that value is less than 1, then our series for a to the n is absolutely convergent. Our second piece states that if our limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is equal to a finite L, but that L is greater than 1, or if the limit as n approaches infinity of our ratio is equal to infinity, then our series will diverge automatically. And then the last piece that our ratio test tells us is if our limit as n approaches infinity of our ratio is equal to 1, the test is inconclusive, so therefore we can't do anything. Like we don't know if it's going to be convergent or divergent. If you do end up in a situation where you get 1, in that scenario, what you would have to do is you have to go ahead and say, okay, this one didn't work. Let me see if there's something else I can do. So we're going to actually go ahead and move on and do a few examples with our ratio test. All right, so our first example is we're going to have our series from n goes to 1 to infinity, of course, and we're going to have n to the 100 times 100 to the n over n factorial. So what we're going to do is we're going to use our ratio test. So every place where we have an n, we're going to plug in an n plus 1. So we're going to get n plus 1 to the 100th power times 100 to the n plus 1 over n plus 1 factorial. And then we're going to multiply that times the reciprocal of our original series. So we're going to multiply times n factorial over n to the 100 times 100 to the n. So from here, let's go ahead and first try to do a little bit of cleanup before we just full on plug it in. Let's see what we can do. Down here we have an n plus 1 factorial in the denominator and an n factorial on top. Well, whenever we have a factorial, we can take one off, so we can get n plus 1 and then multiply that times n factorial, since that means the same thing. And therefore, what we can do is we can go ahead and eliminate these n factorials out of the way. Now let's see what else we can do. We also have our 100 to the n in the denominator and our 100 to the n plus 1. We can break that one up by saying we have 100 to the n times 100 and then divide out those 100 to the nth. So therefore, we're going to be left with n plus 1 to the 100 over n plus 1 times n to the 100. So we're going to go ahead, we take our absolute value, and now we need to find our limit as n approaches infinity. So if we go ahead and play with this a little bit, let's actually go ahead and distribute out that n to the 100 in the bottom to get us n plus 1 to the 100 over n to the 101 plus n to the 100. All right, so if we have this, we can see that in our denominator, we have our highest power is going to be n to the 101. And then we also have in our numerator, of course, we can't really expand this out, but we can just tell by looking at it that our highest power of n is going to be n to the 100th. So, of course, when you're taking limits, of course, we're not going to do L'Hopital's rule, because why would we do that 100 times? But instead, what we could do in this case is we could either divide everything by n to the 101, or we can also just use logic and say that if we have a bigger power on the bottom, then our limit's going to go ahead and go to 0. So therefore, we're left with our limit is 0, and we know that 0, of course, is less than 1. Therefore, our series in this case will be absolutely convergent. All right, let's go ahead and move on and try another one. In this example, we're going to take our series, and it's going to be 2n factorial over n factorial squared. All right, so now let's go ahead and set this up for our ratio test. We're going to plug in an n everywhere we're going to plug in an n plus 1 everywhere we see an n. So we're going to get 2 times n plus 1 factorial over n plus 1 factorial squared times n factorial squared over 2n factorial. So right here on paper, this doesn't look like a ton that we can work with, but we can still go ahead, but let's go ahead and play with this. Let's go ahead and try to see if we can play with some of the, break some of this down a little bit more. We can rewrite the top as saying we have 2n plus 2 factorial. And then we can rewrite the bottom as saying that we have n plus 1 factorial times n plus 1 factorial, and just break up that square. For our other side, we can do the same thing with that n factorial as well. So whenever we're dealing with factorials, of course, the main thing you want to do when you're doing that is you want to subtract, like you want to try to subtract from like your bigger one to go ahead and cancel stuff out. So what we can do here is in the top, we can go ahead and take this piece, and say that we have 2n plus 2 times 2n plus 1 times 2n factorial. So we're just going to take one off of each of those. In our denominator, we can get n plus 1 times n factorial times n plus 1 times n factorial, all times n factorial times n factorial over 2n factorial. So now it's time for us to go ahead and start canceling stuff out. We can get rid of all of our factorials. All right, and then we can see that we are left with 2n plus 2 times 2n plus 1 over n plus 1 squared. So now we can go ahead and take our limit. So we can let's actually go ahead and expand this out first to make this actually a little bit easier. So we can expand our top out to be 4n squared plus 4n plus 2. And our bottom can be n squared plus 2n plus 1. So we can take our limit as n approaches infinity. Of course, from here we can get infinity over infinity. We can divide by n squared to get us 4 plus 4 over n plus 2 over n squared over 1 plus 2 over n plus 1 over n squared. So therefore, we're going to get 4 plus 0 over 1 plus 0 plus 0. So therefore, our final limit is going to be 4. And we know, of course, that's greater than 1. So therefore, we can say that this series is going to be divergent. All right, and then I have one more example for our ratio test before we move on. Because this is another one that looks scary at first, but it's actually very simple. So in this example, they tell us that our first term is going to be 1. And they tell us our a sub n plus 1 is going to be equal to 2 plus cosine of n over the square root of n times a to the n. And essentially we want to find out whether or not the series a sub n is convergent or divergent. So when we look at this, it's easy at first to be like, oh, well, they gave us, it's hard to see what we're looking at. But the thing is, you have to remember, they give us an n plus 1 right here. They give us our n plus 1 right here. And even though they don't tell us exactly what a to the n is, we can still use that to our advantage when we're doing our ratio test. So what we can do is we can actually divide both sides of these by a sub n. So therefore, we can get a sub n plus 1 over a sub n is equal to 2 cosine of n, 2 plus cosine of n, I mean, over the square root of n. So now we can go ahead and take the absolute value of both sides and then take our limit of both sides as well. So we are now officially set up in our form for our ratio test. So let's actually go ahead and look at this. On paper right now, there's really not much we can really take care of. So we're going to have to be a little creative with our solution. So we can see right here that we have a cosine of n. And we know just kind of based, just kind of based on our regular trig that -1 is less than or equal to cosine of n, which is less than or equal to 1. Because remember, cosine, that's their range. So what we can do is we can actually go ahead and use squeeze theorem to go ahead and solve this problem. So what we can do is we can say that we have, on our low end is going to be 2 minus 1 over square root of n. And if we take our limit, and that's going to be less than or equal to our limit of our initial function, and that will be less than or equal to our limit whenever we plug in 1. All right, so now we can go ahead and check our two outer limits and just double check to see that squeeze theorem will work for us in this instance. So if we take our limit as n approaches infinity of 1 over square root of n, we know that's going to be 0. And if we take our limit as n approaches infinity of 3 over square root of n, that will still be 0. So therefore, 0 is less than or equal to the limit as n approaches infinity of 2 plus cosine of n over square root of n, which is less than or equal to 0 as well. So therefore, this limit will also equal 0, which we know is less than 1. Therefore, this series is going to be absolutely convergent. All right, so that's what I have on the ratio test. Let's go ahead and move on to our root test. So our root test is actually going to be very, very similar to our ratio test. Once again, just like the ratio test, it has 3 pieces. The first being that if the limit as n approaches, if the limit as n approaches infinity of the nth root of the absolute value of a to the n is equal to some finite L, and that L is less than 1, then the series of a sub n is going to be absolutely convergent. Part 2 states that if our limit of the nth root of the absolute value of a is equal to some finite value which is greater than 1, or if our limit is equal to infinity, then the series A is divergent. And then our last piece is going to state that if the limit as n approaches infinity of the nth root of the absolute value of a is equal to 1, then just like with the ratio test, the test will be inconclusive, therefore test fails, you have to go and restart. All right, so let's actually go ahead and go through so let's actually go ahead and go through a couple of these. All right, so for our first example, we have our series, and it's going to be n squared plus 1 over 2n squared plus 1 to the n. So we see a power to the n, so that's a pretty good indicator to go ahead and use our root test. So what we're going to do is we're going to do our limit as n approaches infinity of the nth root of n squared plus 1 over 2n squared plus 1 to the n. That nth root and that to the n will cancel out, so therefore we're going to take our limit as n approaches infinity of n squared plus 1 over 2n squared plus 1 . We're going to get infinity over infinity initially. You can divide by n squared or do L'Hopital's, whichever floats your boat. And we can get, I'm just going to divide by n squared. We're going to get 1 plus 1 over n squared plus 2 plus 1 over n squared. So therefore, we're going to get 1 plus 0 over 2 plus 0. So therefore, our limit is going to be 1/2. When then that is less than 1. So therefore, we can say that this series right here is absolutely convergent. All right, so now let's go ahead. So that one was pretty simple. Let's try another one that's a little harder. So in this one, we're going to have negative 2n over n plus 1 to the 5n. We see that exponent n, so that's a good idea to go ahead and do our root test. All right, so we're going to go ahead and, not our series. Take our limit as n approaches infinity of the nth root of the absolute value of negative 2n over n plus 1 to the 5n. Those two n's will go ahead and cancel out, leaving just the 5 up in the exponent. So now we have our limit as n approaches infinity of the absolute value of negative 2n over n plus 1 to the 5th. All right, so I believe we actually, so this one just as it is, I mean, you could work with it. Or what we can, you could work with it as is this way, or we can actually do, I believe we used this theorem like a couple weeks ago to where we can actually go ahead and look at the inside and then take that, like work inside out with our limit essentially to make this a bit easier. So we can go ahead and take our limit as n approaches infinity of negative 2n over n plus 1. We're going to get negative infinity over infinity. Do L'Hopital's. We're going to get negative 2 over 1. So negative 2. So now we start working back out. So we're going to raise that up to the 5. So we're going to get negative 32 and finish working out, working that back out to the beginning. Take our absolute value. So we get 32. Well, we know 32 is going to be bigger than 1. So therefore, we can say that this series is going to be divergent. All right, so that's pretty much all I have for section 11.6. Neither test is really that complicated once you kind of get used to working with the numbers. It's a lot of algebra for both of these. But the tests themselves, though, aren't really that hard, aren't that bad. So now we're going to go ahead and move on to section 11.7. And this is going to be strategies for testing series. All right, so this section is essentially just one big review section over everything we've covered in chapter 11. So essentially what we want to do right now, what we're going to do here is we're going to essentially kind of compile just a list of all of our tests and kind of get an idea of when to use these. So back whenever we actually did exam 1, around when we did exam 1, we had a section like this for integration. And whenever we did that for integration, we said look at the form of your integral first, and then use that to determine what method you're going to use to integrate. Well, we can think of it in the same way whenever we're doing with series. You want to look and see what form our series is in, and then go ahead and then pick the test to match that, rather than just trying a whole bunch of tests and wasting time. So let's go ahead and start. If we have the format to where we get 1 over n to the p, that's obvious hint, that is a p series. And of course, remember p series, if P is greater than 1, it's convergent. Another test that we've covered pretty extensively is going to be our geometric series. So we're going to have our series with a times r to the n minus 1. Or we can get it in the format n to 0 of a times r to the n. Either way, with both of these, you know you're going to go to a geometric series. And to test for, and of course, as a reminder, to test for convergence with geometrics, if the absolute value of r is less than 1, it's convergent. Method 3 that we could use. If the series resembles or like has a similar form to a P series or geometric, what you want to do here is you're going to go ahead and use a comparison test. And remember with our comparison test, remember we had two. We had our direct comparison and we had our limit comparison. So yeah, that one's a pretty easy one just to go ahead and just, if you see it, just know, if you see it and it's like, or if it just has like an extra thing, like let's say you have like natural log, like let's say you have something like natural log of k over, natural log of n over n, you can maybe try comparing that with 1 over natural log of n. And then see where that takes you. Number 4, and really I feel like this one is kind of the most obvious one to check first. Like normally it's, I would say like don't really worry about order, but really I would say like don't go out of your way, but this one's pretty obvious. If you can tell that the limit as n approaches infinity of our sequence, like just the sequence, not the series, does not equal 0, you're going to use our test for divergence. And then just say that's not 0, therefore it's divergent. Like I wouldn't go too far out of your way to prove that. If there's like another way that'd be a little bit better and could actually show if it converges. But I mean, there's some cases where you can just look at it and you can be like, oh, I have 4n squared over 3n. You know that's going to be divergent just looking at it. Five is another. Okay, so our next test that we have is also another pretty easy one to recognize. Is whenever we have -1 to the n minus 1 times b sub n, or whenever we have just -1 to the n times b sub n. With that one, you just know that's going to be an alternating series. Now for that one, you may have to go back and apply another test just to see if it's going to be conditionally or absolutely convergent, but alternating series though is a really good place to start. All right, now we have test number 6. So if you have anything like this, if you have a factorial, if you have something to the n power, or you have like some combo of like products, of like a lot of products, that's going to be a hint to go ahead and do your ratio test. Now, just a quick thing to check before you start your ratio test. If it could be like just double check your series equation and just double check to make sure to see whether or not it could be written as a p series, because if it could be written as a p series, ratio test will automatically fail. Like, I mean, it's not a huge deal if you don't like. It's just that's gonna waste time. Let's say like you may be on an exam and you need to go ahead and get that problem done. Then that may be wasting time. That may just be wasting time, like just for you to get, oh, test fails, whenever you could have just looked at the beginning and been like, oh, let me just rearrange this. Okay, we're good. Our next form that we could get is if we have our sequence is written in the form to where like we have like a sequence weight raised, like all of it raised to the n. That's a pretty clear indicator to go ahead and use your root test. All right, and then our last test that we have is going to be if we can write our so let's say we have an a sub n is equal to f of n, to where like we can write our sequence as a function. If we have it like that, to where our integral, where we can easily integrate from 1 of f of x dx, like if that's easy to evaluate, from there you want to go ahead and do your integral test. All right, so that is actually pretty much all I have for this week. Neither section was particularly long. I mean, I can go ahead and maybe do like a couple of examples, like just to kind of just be like, hey, if you see this, like try XYZ test, just give me, actually I think I will go and do that for a couple minutes. Just give me a minute to get the book pulled up. All right, I have some problems that I have pulled up on my iPad now. So let me go ahead and just kind of write some out, and then we can just kind of say like, hey, like look at this. This is how you can rewrite this. All right, so let's say this is our first example. Yeah, we're gonna have, in this one, we're gonna have, it goes from 1 to infinity of n minus 1 over n cubed plus 1. Well, if we look at this, this one's actually pretty easy. We can go ahead and split this up. And then what we can do is we can do n over n cubed plus 1 minus 1 over n cubed plus 1. And then we can go ahead from there and then do some comparison. And from here we can do a mix of comparison plus a p-series to make that really easy. So, because that'll be pretty easy just to go ahead and plug that in and look. Since we have a power on the bottom, that's kind of like really easy to like look at that and cancel and just try to cancel stuff out. All right, let's say we have all right, let's say we have this one. N to the 2n over 1 plus n to the 3n. Well, for this one, we have a couple things we could do. We can go ahead, we can see how we have like n's on the tops and bottom. We can also look and see that, so yeah, if we look at that, we have like n's on the bottoms. We also have an x to the n in there as well. So for this one, what I would, and you could also maybe rewrite this. So for this one, some couple roots that you could try could be root test. You can try a root test. You can go ahead and you can maybe write this in a geometric, but if not, wouldn't be that pretty though. Yeah, that's not really going to be a good form for your geometric. You could maybe try to do a ratio test, but I think for this one, your root test just is probably going to be your best bet with taking care of this. Like, and this is just from looking at it. Like, I'm not going to like go through like and solve all of them, but this is just like from what I'm getting from right now. Let's see, we have this one. All right, so from this one, there are technically a couple different ways. You could maybe go ahead and maybe try to use an alternating series since we do have that -1 in there. But what would probably be a better one to do is to actually go ahead and use our ratio test since we have an exponent in and we also have an n factorial. Like, I mean, if you want to try alternate, alternating series, go ahead and knock yourself out. But I think ratio for this one, since we have that factorial, is just kind of a big hint to go ahead and maybe look at your ratio test. And then let's see what else we have. All right, so we have this one. One over n over the square root of the natural log of n. So for that one, what we can do, since we can, since if you look closely, we can kind of have this 1 over n here. So this is another one to where you can kind of go ahead and do a mix of comparison and a p-series. We also have another one that is fairly similar. Let's say we have something like this. It's where we have -1 to the n natural log over square root. We see that -1, so a good place to start could be your alternating series test. And another thing for this one, since we also see that square root of n on the bottom, that's another one where you can maybe also look into maybe doing comparison plus a p-series. All right. Yeah, looking at this, I think that's pretty much all I have for today. So good luck on y'all. Yeah, so just good luck on y'all's future assignments and good luck on y'all's exams. I know exam season's pretty crazy right now. All right, so have a great afternoon, guys.